Hello, welcome to lecture 18 of Elec Eng2CI5. In this lecture, we'll be discussing inductors, and an inductor is a very important component in electrical engineering. It's capable of storing magnetic energy. So we have seen in the previous lecture what a capacitor is. A capacitor is a component capable of storing electric energy in its electric field. The inductor stores magnetic energy in its magnetic field. And so in this lecture we'll discuss what's an inductor, what is the relationship between the voltage and the current, and what is the expression for the energy stored in an inductor. And once we are done with this, with lecture 17 and 18, the introduction to capacitors and inductors, we'll start now to move to analyzing transient circuit that has one or more of these components, capacitors and inductors. Okay, first we start by discussing what's an inductor. An inductor is simply a coil. So we have a wire that has a number of turns, and we have this wire. It has some core inside, so we have these turns surrounding this core, and this core is usually made of a material with high permeability. Permeability is a property of matter. It describes the ability to magnetize the material. So things like steel and iron and so on, they are good candidates for such a magnetic core. This core can be a cylinder like this one. So this is a solid cylinder. It's made of this magnetic material, or it can be a toroidal shape like this one. So you have this number of turns around this toroidal shape, and this will be an inductor as well. An inductor is a device that's capable of storing magnetic energy. So what happens when you connect a source to this inductor? Say here, if you connect a voltage source of some sort, okay, there'll be some current injected in these turns. Okay, so there'll be a current flowing in these turns, and this current is gonna create magnetic flux phi. We call it phi. It's a magnetic field inside the core, and this magnetic field, it's the one that stores magnetic energy. Okay, and we'll show you that there is a relationship that relates the voltage that's between the terminals of the coil or the inductor and the current flowing through the inductor. There is a relationship between them, and we'll see again it's not a linear relationship like in the case we had with resistors, but rather one of them is the derivative of the other, and you can get the inverse relationship. It's going to be an integration. Okay, so we're going to see this very soon. So what happens is that when you have a current flowing in a magnetic field in the inductor or this coil, it creates a magnetic field or magnetic flux phi. And in this course we deal only with linear inductors. Linear inductor is given by this relationship: phi is equal to Li, where L is the inductance. So the higher the current flowing the inductor, the higher the magnetic field inside the core of the inductor, and the constant of proportionality is the inductance, and it has units. We call it Henry. Now the basic relationship relating the voltage and current comes actually from an electromagnetic law called Faraday's law. Faraday's law is simply saying if you have an electromagnetic structure and the flux going through that structure phi is changing with time, then this rate of change d phi by dt will create a voltage difference in that structure. And here we have this structure is simply the coil or the inductor that we have. So there will be a voltage difference between the terminals of the coil, and is equal to the rate of change of the flux, but the flux is equal to Li. So we get this relationship here, that V of t is equal to L di by dt. So, and this is one of the two fundamental relationships you have to remember for inductor. The voltage between the two terminals of the inductor is proportional to the rate of change of the current, and the constant of proportionality is the inductance. Okay, so the inductor usually it has this circuit symbol here. I can try to draw it for you. So it has this circuit symbol. Okay, so this is a current flowing in I, and this is the voltage across it. And again, we apply the same notation we use for a capacitor. We use we assume that this terminal is positive to this one. The current is assumed to be positive. It's flowing from the positive terminal to the negative terminal. Okay, so when this current flows inside the inductor, it creates magnetic field, magnetic flux here in the core, and this magnetic flux it creates a voltage V, and the voltage V between the terminals is equal to the rate of the change of the flux. And again, when you study electromagnetics, course electromagnetics, you spend some good time discussing Faraday's law and how it was derived and its applications and so on. So the first relationship we got is that the voltage between the terminals of an inductor is equal to the inductance multiplying the rate of change of the current. This one is easy to apply. So if you know the current as a function of time, differentiate it, multiply by L, you have the voltage. But what if we have the voltage, would like to get the current? What we'll do is that we'll integrate both sides, multiply by dt here. Okay, you integrate both sides. And as I mentioned in the previous video, if you integrate, you change the parameter of the integration from t to tau, because the bounds that you are integrating are the bounds of the integration, this one and this one, they have t in them. So what you are doing, you are saying the integration of the current from the very beginning to time t is equal to 1 over L, the integration from the very beginning to time t. This is di of tau, and this is v of tau d tau. Okay, we apply the rules of integration. The integral of di of tau will give us I of tau, both upper limit minus lower limit. You get I of t minus I of minus infinity. If you take the current at the very beginning was equal to 0, then this gives you I of t, and this becomes 1 over L, the integral from minus infinity to t v of tau t tau. So what does this relationship say? It says is that you have, what this relationship says is that the current is the integration of the voltage, okay, and you have this constant of proportionality between them. So when you are calculating the current from the voltage, you are carrying an integration. And again, we remember that we took at minus infinity in the very beginning, we took the current to be equal to 0. If you are doing your calculation but you want to start at some other limit, you have to use the current at this initial limit as a starting point, and I will show at least one example on that. Okay. So this slide actually summarizes this. What if we are told that at time t naught, which is not minus infinity, the current is equal to I naught. Then what you have to do, you have to divide the integral from minus infinity to t to an integral from minus infinity to t naught, and the integral from t naught to t. This one here, this part here, gives you the current at t naught. This one here, this part gives you the current at t naught. Then you can simply say the current at any time t is equal to the current at time t naught plus 1 over L, the integral from t naught to t v of tau d tau. Okay, so just remember this, that because you're doing an integration, you have to pay close attention to the bounds of your integral. But the differentiation is easier. So going from the current to the voltage is easier because you don't have to worry about the initial values or anything like that. Okay, let's take a look at one example. We're given here some current waveform. This is in milliseconds. Everything is milliseconds, and everything is in milliampere. So the current goes from 0 up to 1 milliampere, stays at 1 milliampere, and then it goes down from 1 milliampere to minus 1 milliampere. Stays constant, then goes down to 0 again. And this happens 10 milliseconds, 20 milliseconds, 30 milliseconds, and so on. We would like to find the voltage across the inductor, and the inductor value is equal to 0.5 Henry. Okay, so L is given for us. Of course, when you have something like this is the easy part, because you know the current, you want to get the voltage, but the voltage is equal to L di by dt. This is from Faraday's law. Okay, V is equal to d phi by dt, but this is a linear inductor, so phi is equal to Li, so V is equal to L di by dt. So now we'll start to differentiate, and differentiating the current means getting the slope of the current. And as you can see here, there's a slope in this part. We can find the slope here. This is 10 milliseconds, this is 1 milliampere, so the slope here is 0.1. The slope here becomes 0. Again, it goes from 1 up to 0 in 10 milliseconds. So the slope here is minus 0.1, because it's minus 1 over 10, so it's minus 0.1. The slope here is still minus 0.1. The slope here remains constant at 0, and then start to increase again from -1 to 0. So the slope here is positive, and it's equal to the difference that we have here is 1 divided by 10, so it's 0.1. So remember the slope, which is di by dt, here is 0.1, it is 0, it is minus 0.1, it is 0, it's 0.1. We're going to use this one in order to calculate the corresponding voltage for this waveform. Okay, so this is what we have. This is really the circuit that we have. We have a current source. It's injecting current inside the coil. And this current source is varying with time. It's not a constant current source like the one we have seen in all the DC cases. It's changing with time according to this given profile. Okay? And of course goes down to 0 afterwards. So our target is to find V. Well, we know that from an inductor relationship, V is equal to L di by dt. And the L is equal to 0.5 Henry, so this is fine. The slope here in this part, as we agreed, is 0.1. It is 1 millihenry. Sorry, it's 1 milliampere divided by 10 milliseconds, so it's 0.1. So in this part, the voltage between 0 up to 10 milliseconds, the slope is the same, it's 0.1. Then the voltage is equal to 0.5 multiplied 0.1 is equal to 50. It's 0.05 volts, or it's 50 millivolts. Okay, this between t equal to 0 and 10 milliseconds in this part. Now in this part between 10 and 20 milliseconds, the current graph is flat, so the slope is 0. So this means di by dt will be 0 and the voltage will be 0. So the voltage will be equal to 0 volts between 10 and 20 milliseconds. Okay, now between 20 and 40 milliseconds, the slope becomes negative. The current is decreasing. What is the slope here? It goes down from 1 milliampere to 0 milliampere in 10 milliseconds. Then the slope here is equal to -1 over 10. So it's equal to -0.1. So in this part, the voltage is equal, you can see it's 0.5 multiplying -0.1 will be equal to -0.05 or -50 millivolts. This is between 20 and 30, and it actually continues as well between 30 and 40. Between 30 and 40 you have the same slope. So I bought it here at 30, but effectively this slope is actually continuing as well to 40. So I may as well write this one between 20 and 40. You can repeat the same steps for the rest of the graph. And if you try to plot now, this is a current that's given from 0 to 1 milliampere, 0, -1 milliampere, and then goes down to 0 again. You see that the voltage here is 50 millivolts in this part. It goes down to 0. It goes to -50 millivolts because the slope here is negative, and then it becomes 0 again, and then this is a positive slope, becomes 50 millivolts again. And of course, if this continues, if this waveform continues, you're gonna get more periods of this voltage. What does this tell us? The voltage across an inductor can be discontinuous. You can see at this point it went down from 50 millivolts to 0 in no seconds. But the current going through the inductor has to be continuous. You can see it goes down from if you goes down, it has to go down from 1 milliampere. It cannot go down from here. Okay, because this means you have this continuity, and actually there's one physical reason for that as well. Because if you write that V is equal to L di by dt, if di by dt is not continuous, then this slope at one point becomes infinite. The slope here is infinity. It's actually minus infinity here at this point. It's minus infinity. It goes down from 50 millivolts to 0 in no time. So if this is minus infinity or infinity, this means that you need infinite voltage to do so, which is not a physical thing. This is why the current going through the inductor will have to be continuous, but the voltage across the inductor can be discontinuous. Now, this is opposite to the case of the capacitor. In the capacitor, the voltage has to be continuous, but the current can change its direction suddenly. So this is fine. Current here in an inductor is always continuous. Voltage can be discontinuous. In a capacitor, the voltage is always continuous, but the current can be discontinuous. Okay? Very important to always compare the inductor and the capacitor against one another. Okay, let's see one more example. We are giving the current passing through an inductor. It's 0.1 sine 200 by t. We would like to find the inductor voltage as a function of time. So, and the inductor value is 0.1 Henry. This is an easy example as well because I want to get the voltage from the current, but the voltage is equal to L di by dt. Then it's just a matter of differentiation. I don't have to worry about limits as in the case of the integration. It's very important to realize why we keep on showing you examples about sinusoidal waveform. This is a sine waveform. It's changing sinusoidally with time. Because later we'll be analyzing circuits for sinusoidal inputs. This is called the AC analysis, and it's a very important case in electrical engineering. So just keep in mind now we're just showing the final result, but later we'll be reminding you of this result because it will show up again when we discuss phasors and current in AC circuits. Okay, let's take a look here. This is exactly what we have again. We have a current source. It's injecting current in an inductor. And this current source here is sinusoidal, changing with time. So part of the time the current is going this way, part of the time is going this way. So one half of the cycle is going this way, the other half is going that way, and so on. So we'd like to see what will be the corresponding voltage. The expression is V is equal to L di by dt. L is 0.1 Henry, I is 0.1 sine 200 by t. Again, 0.1 by 0.1 will give you 0.01. The derivative sine 200 by t will give you 200 by multiplied cosine 200 by t. If you multiply this one by 0.01, you get 2 by. So if the current is a sine function, the voltage is a cosine function. Okay, and of course you have different amplitudes, and this amplitude will depend on the frequency and on the inductance. Okay, you can see the frequency itself. This is omega. This is sine omega t. This omega here, which is radian frequency, and radian per second, radians per second does affect the value of the voltage, the amplitude of the voltage. Okay, so this amplitude of voltage depends on two things: on the value of the inductance, the value and the frequency as well of the current waveform. Okay, so what does this mean? This means that the voltage leads the current, as we explained before in the case of the capacitor. So in the capacitor case, I mentioned to you that the current leads the voltage. Here there is also a lead-lag relationship between the inductor current and voltage. You see the voltage is a cosine. This means that the current is a sine. And as we agreed from the case of the capacitor, the cosine function is ahead of the sine function. This figure here helps shows you what I mean. This is a current. This is the current we started with. This black, and this is the voltage we got. Okay, they have different amplitudes, so I'm drawing them in the same graph, but they have different amplitudes. Okay, you can see at time 0, the voltage is at its peak, while the current is still at 0. The current will take another quarter cycle until it reaches its peak. So if you compare this point here to this point here, you'll see that the peak of the voltage appears ahead of the peak of the current. So this means that the voltage leads the current. Okay? So remember this, in an inductor, the voltage leads the current. When we have sinusoidal inputs, I mean. And for the capacitor, it is the other way around. It is the current that leads the voltage. Later, you will see this appearing in when we analyze AC circuits, but keep this one in mind for now. Okay, now we get to a little bit harder problem. Why? Because I'm giving you now here the voltage, and I'd like to get the current. Okay, so the voltage waveform applied to an inductor, it looks in the way shown here. It is 0 from minus infinity up to 2, and then it increases gradually and slowly up to 2 volts between 2 and 5 milliseconds, and then it goes down from 2 to 0 volts between 5 and 6 seconds. These are seconds, or everything is seconds. Okay, and the voltage also is in volts. The inductance value, or the value of the inductance of the inductor is 2 Henry. Would like to find the current at any time, and we are given that I of 2 is equal to 0 ampere. Remember the expression that we have, which was the integration from minus infinity to t. Assume that the current at minus infinity is equal to 0. Here we have to take into account that the current at 2 is equal to 0 ampere. So this is an integration. We have now to integrate the voltage to get the current. Let's see how we're going to do this integration. Okay, first what I started with, I wrote an expression for this figure, for this graph here. This is a linear graph. The current, the voltage, sorry, this is the voltage. It increases gradually from 0 up to 2 volts between 2 and 5 seconds. So you can find the expression of this line. The voltage here is simply equal 2 over 3 t minus 2. There is, of course, maybe you should remember this from your simple math courses. If you have 2 points on a line, you can write the equation of this line. And here we have 2 points. This point here times 2, voltage is 0. This point here times 5, voltage is 2. So I can write this expression here for the voltage is 2 over 3 t minus 2. So I'm gonna go to my basic law here that the current is proportional to the integration from minus infinity to t v of tau d tau. But I restart everything as 2. So I'm gonna divide this to an integral from minus infinity to 2 and the integral from 2 up to t. This whole term gives me I of 2. As we agreed before, this is I of 2. This is the current that was accumulated in the inductor until time 2, which is equal to 0. Would luckily is given to equal to 0. If it's not 0, you have to put this constant there. And this what I'm going to be integrating. I have to integrate from t up to t, from 2 up to t, v of tau d tau. Notice that because the voltage has a number of functions, here it is 2 over 3 t minus 2, but here it's minus 2t plus 12. So I cannot do this integral at one shot. I can't do that. I have first to find the integral from 2 up to t, where t is between 2 and 5. So this will allow me to find the current between t equal to 2 and t equal to 5. Okay, and this is what I did here. I replaced v, I wrote v of tau is 2 over 3 tau minus 2 d tau. Remember, you are integrating relative to tau, and whenever you have t as one of the integral limits, it is usually the way they change the parameter of the integration to avoid confusion. Okay, so this is v as a function of t. I simply replace t by tau here. So this will give me 2 over 3 tau minus 2. So let's integrate this one between 2 up to t. The integral of tau will give me tau squared over 2. The integral of 2 will give me 2 tau. Substitute upper limit minus lower limit and then collect the different coefficients. Okay, so I did my integration here. I multiplied by 2 over 3. Actually, I already got 2 over 3 first, and then I integrated. The integral of 2 tau will give me tau squared. The integral of 4 over 3 will give me 4 over 3 tau. Both upper limit, this will give you t squared over 6 here, multiplied by 1/2. And this one will give me minus 4 over 3 t multiplying 1/2, so minus 2 over t over 3. Now, if you put 2, you get 4 over 3 minus 8 over 3. Okay, let's see here. So this, yeah, so this becomes this one, and because you put upper limit minus lower limit, so this will give me 4 over 3 for the upper limit. So this, if you put 2 here in this term, according to my calculations, I got 2 over 3 here. Let me double check this one. So this becomes 4 over 3, and this becomes minus 8 over 3. Okay, somehow I feel there is a negative sign here. Okay, I believe there should be a negative sign here. So let's I believe there is a negative sign, because this will give me 4 over 3 minus 8 over 3. So let me correct this one as we go. Maybe this is a typo in my solution. This becomes minus here. Okay. Okay. So so if we proceed that way, you are able to find your initial current at time 5, because remember, we have to find also the voltage between 5 and 6. So let me backtrack again. We found here through this integration I of t has to be between 2 and 5. It is given by this expression here. Actually this one is correct. Let me backtrack again. This one is correct, and the reason that it's correct is that this is a lower limit. When you put the lower limit, you have to include the negative sign. So it's okay. It's not really wrong. This will still be positive here. Okay, I forgot about this this negative sign. Okay, so what's happening when you put the upper limit? Everything will be put with its sign, but when you put the lower limit, you have to change the sign. So this becomes 8 over 3 minus 4 over 3. So this is fine now. 8 over 3 minus 4 over 3 will give us 4 over 3 multiplied by 1/2, you get plus 2 over 3. So this is fine now actually. This is 2 over 3 and this is 2 over 3. Okay, so we found I of t. I of t is the current flowing between 2 and 5. Okay, this is good. So we can now find what will be the initial current for the next step, because we have to integrate between 5 and 6 as well. Okay, remember we have to find also the current between 5 and 6. So we need the initial value at 5. Remember, you are doing an integration when you calculate the current from the voltage, so you need the initial value. So so what is happening here is that I have to calculate I of 5, put here t equal to 5. You get 25 over 6 minus 10 over 3 plus 2 over 3. If you collect all this, take 6 as a common denominator, will give you 25 minus 20 plus 4. So this is going to give me 29 minus 20 is going to give you 9 over 6 over 3 over 2 ampere. Okay, now we go to the second part. Between 5 and 6, we would like to get the current from the voltage. Okay, the current is 1 over L, the integral from minus infinity to t v of tau d tau. This is a general law that we have, okay? But I'm now starting my integration from 5. Then I can write this one, the integral from minus infinity to 5. Okay, so I can do this one here as the integral from minus infinity to 5, v of tau d tau. And the integral from 5 to t, v of tau d tau. This term here gives me I of 5. Okay, this is the current that accumulated inside the inductor between minus infinity and 5. This is the current that accumulated in the inductor between minus infinity and 5. And this one we already know. This is 3 over 2. And this is why when you are doing integrals, you are calculating the current from the voltage, you have to keep track of the current at your start at the start of your integration. So in the beginning we started from 2, we have to get I of 2. We finish this part. Okay, now we start from 5, we have to get I of 5, and then we proceed. Okay, so now I of t is equal to I of 5 plus 1 over L, the integral from 5 to t v of tau d tau. This one here 3 over 2. I replaced the v of t by its expression for the second line, which is minus 2t plus 12. But here my variable of integration is tau, so I wrote it as minus 2 tau plus 12. Again, you will have to integrate this term, and then you have to I actually multiplied first by 1/2, so this becomes minus tau plus 6. If you integrate minus tau, you get minus tau squared over 2. If you integrate plus 6, you get 6 tau. Both upper limit minus lower limit, so the upper limit is going to give me minus t squared over 2 plus 6t. The lower limit will give me minus. Now I remember now I have to include the minus sign. This will give me here minus 30 plus 25 over 2. And then you have to add 3 over 2 as well, and this will give you minus 16. Okay, I think I double checked these numbers, they are fine. This is valid between 5 and 6. Why is it valid between 5 and 6? Because we use the expression of the voltage between 5 and 6, which has negative slope. So what will be the last value of the current reached at the end of this period? It's I of 6. You put here t equal to 6. So you get minus 36 over 2. This will give you 36. This will give you minus 16. You end up with 2 amperes. Okay, please double check these answers, but I believe they are correct. So now if you want to check the current, the voltage and the current, this is a given voltage. It's rising up to 2 and then it's going down from 2 up to 0. You will see that before that the current was 0 because there was no excitation. This actually, just let me backtrack. This is how the circuit looks like. Now we are applying a voltage to the inductor. Okay, and we would like to calculate the current flowing in the inductor. So this is my target here. Find I of t. This is really my target here for this case. Okay, so in the beginning there was nothing, there was no voltage, nothing. So the voltage was 0, the current was 0. When you started to apply a voltage and you applied it in a linear way, it's ramping up. The current starts to increase in a non-linear way. It's t squared, it's a function of t squared. And we found out that at point 5, t equal to 5, it reaches 3 over 2. Now, in the second period, you are still accumulating area under this graph. There is still positive area, so the current will continue to increase. It will increase from 3/2 to 2, and we find the expression. It's another quadratic one, but with different coefficients, and it reaches 2 ampere. After that, the current will remain the same. The current will not disappear, even though the voltage reaches 0. But the current will still continue to flow. It's now a DC current going through the inductor. Okay? And this current will continue to flow for infinity. Why is that? Simply because it is stored in the magnetic field of the inductor. It is the same current going through the loop. So and here you have this current flowing. There is nothing that would stop it from continuing to flow. Okay? Even though the voltage reaches 0. The voltage across, and this is something you will know, and it was mentioned in one of the slides. If you have DC, then the inductor looks like short circuit, but still a current going through it. It's short circuit, but still a current going through it, and it's accumulating magnetic energy. Okay, it's very important to remember that. So this is very interesting. So once you give it this current, this current is going to be there forever. Of course, in reality, these wires have resistances, and these resistances start to consume power, and then the current going through the inductor will start to decay with time, gradually and slowly. But of course, if you can build a perfect inductor, this current will continue to circulate at a value of 2 ampere forever. Okay. Now we move to discuss the last point of this lecture, which is the power and energy in an inductor. We agreed before in previous lectures that the power dissipated or the power delivered to any component is V of t multiplied by I of t. And here we know that the voltage is equal to the inductance multiplied by the rate of change of the current. Okay, so this one you can calculate the instantaneous power. This is called the instantaneous power. If you want to change, if you want to calculate the energy, you have to integrate this power over the period of interest. We want to calculate how much energy was delivered to that inductor. Okay, and this is what we're going to be seeing in the next slide. And this expression simply says what I stated before, that the current going through an inductor will have to be continuous, while the voltage through the inductor can be discontinuous. And it is the other way around when we talk about capacitors. This is a very simple derivation, not any different from the one we did for capacitors. If you want to get the energy at any time t, you integrate over all power from minus infinity to t. We assume we start at minus infinity, there was no power at minus infinity. So you multiply the current with the voltage, but the voltage is equal to the inductance multiplied by the rate of change of the current. D tau will cancel d tau. You can integrate relative to di of tau, and I think I have a mistake here. Yeah, I think this one is definitely a mistake because this one is di of tau. Okay. Let's see here. Actually no. Actually, this. Let me take a look here. So there seems to be something missing here. Yes, I guess I know what is missing. Okay, so this integration here, this is the integral that we have here. This is really the integral. I'm gonna write it here again. It's L, the integral from minus infinity to t, I of tau, di of tau. Okay, so I have a mistake here because my variable of I'm integrating relative to I itself. Okay. So when you integrate I of tau relative to I, you're gonna get 1/2 I squared. Okay, you're gonna get 1/2 I squared here. So this is the integral you're gonna be carrying out, and this will give us the expression for the energy stored in the inductor. It is the energy at any time t is 1/2 L multiplied by the value of the current value of the current squared. And this is very similar to the one that we got from the capacitor. The energy stored in a capacitor is 1/2 multiplied by the capacitance multiplied by the voltage squared. So you see there is some sort of a duality between the inductances and the capacitances. Okay, so we'll see how we're gonna proceed with this one right now. Okay, let's have this example. We have a circuit. We are told that the energy stored in this circuit is 80 millijoule. Would like to find the value of the inductance L. We know that this circuit is a DC circuit. So for a DC circuit, And as I mentioned earlier, a capacitor will represent the open circuit, because if the current is not changing with time, okay, then the capacitor will be actually, let me show you where's the origin of this one. We said before that for a capacitor, I is equal to C dV by dt. Okay, so if the voltage does not change with time, then this term is zero. It's DC. This term is zero. If this term is zero, means there is no current going through it, because I is zero. I is zero means that this is open circuit. For the inductor, it is the other way around. The voltage will be zero, means that this is short circuit. So what effectively, when you analyze this circuit, this is short circuit, and this one here is open circuit. Okay, for DC analysis. In DC analysis, an inductor is a short circuit, okay, and a capacitor is an open circuit. So we can determine, if you know the value of this capacitor, we can find the energy stored in it, and we can find also the energy of the stored in the inductor. This is 1/2 L multiplied I squared, and the I is the current flowing in this branch. Remember, for a DC circuit, the circuit looks like this. It is 1 ampere. You have 1 ampere, okay, current flowing 1 ampere. You have a resistor of 200, and then you have another resistor of value 50 ohm. Okay, this is a capacitor, it's open circuit. Okay, the inductor is here in this part, and it's short circuit. Okay, so neither the capacitor nor the inductor will appear in the DC circuit, because the capacitor is short, the capacitor is open, and the inductor is short, but they still store energy. Okay, this is very important. So what we have to do right now, we have to find the voltage across this open circuit here, which is the voltage across the capacitor. We have to find the current flowing in this short circuit here, which is the current flowing through the inductor. Okay, so let's see how we're going to do this in the next slide. So we do the analysis of the circuit. We can find the voltage. This is DC analysis. This is the capacitor, this is the inductor. For DC, the inductor is short circuit, capacitor is open circuit. So you analyze it as a regular DC circuit with two resistors in parallel. You can find this voltage here. This voltage here is equal to this current source multiplying by this parallel combination. So it's 1 ampere multiplied 200 by 50 over 200 plus 50. So this voltage, the voltage across the capacitor, is 40 volts. Okay, remember, the capacitor represents open circuit, but this does not mean it does not store energy. It's actually storing energy, but it does not allow any current to go through it anymore. Okay, because it's DC. The current going through the inductor, we can use current division. The current, this one here, is equal to 1 ampere multiplying 200 over 200 plus 50. So it's 0.8 ampere. So we know the voltage across the capacitor, the current going through the inductor. The energy stored in the capacitor from the previous lecture is 1/2 C VC squared. But C is given, and I know what is VC. I already calculated that. So this is 80 microfarad, this is C, and this is the voltage we calculated here, 40 volts, so 40 volts squared. So I know what is the energy stored in the capacitor. But the total energy stored in the capacitor and the inductor is 80 millijoule. So this means that the remaining 60 millijoule went to the inductor. So I know the current going through it. I know the energy stored in the inductor. I can get the value of the inductance. So the last step here, I know that I have 16 millijoule were delivered to the inductor. The inductance value is my unknown. I know the current going through it's 0.8 ampere. I square this one, multiply by 1/2, and then I can get the inductance. It's 0.05 Henry.